So let me just repeat that for those who are not here and will join us later. We will have our midterm. We set up the date for October 26, but you can email me if you find this date inconvenient, and I will update if I receive a lot of requests for scheduling this. But if I don't, then it will stay on October 26th. Also, as I already said, you guys can reach out and let me know anything, any concerns that you have, and I'll try to accommodate. Also, I want to say that the next midterm will be your chance to improve over your first midterm. Because as you know, I just take the best score out of the two, and that counts towards your overall course grade result. But I mean, you have to do. I mean, I cannot do anything after the second midterm. So please prepare for the midterm and do your best, because I will not be able to help much after the second midterm. Of course, you can improve in the final. That's definitely true, but for the midterms, I won't be able to do anything. Also, there is no extra credit. I don't have any extra credit in this course. Okay, now let me start. Chapter 6 is 5. This chapter is about hypothesis, tests for the bivariate linear regression model parameters. Okay. Let me remind you guys our bivariate linear regression model that has this form. Why is this a bivariate model? Can you guys tell me? Please try to be involved. That will help me proceed at a good speed, because then I will realize, then I will adjust the speed. So why is this model a bivariate model?
Can you define what bivariate means?
Bivariate means that it only includes two variables.
The model includes two variables as well, which is x and y, and one is dependent on the other.
Yes, and because it includes two variables, one of them is independent, as you said, and the other is dependent variable. That's why the model is bivariate. Okay. Variables x. Oh. How do I do this? One is x and the other one is y. So the parameters are beta 0 and beta 1. Do we know these parameters? No, we don't know them, and we want to obtain estimates of those, and we want to obtain best possible estimates of those. What is UI?
Residual?
No.
Garbage.
Very good. So guys, there's a big difference between a disturbance and a residual. This is one of the key things to understand in this course. So that you know what you are doing when you are estimating models. So how do we define the disturbance? That's yi minus conditional on xi. How do we define the residual? Guys,
Is it yi minus y bar I?
no, it's yi minus y hat I.
Y hat, yeah.
What do we call this y hat?
An estimator?
We call it a fitted y. And this is what? Actual y. Of course, for observation I. Guys, am I clear?
Yes.
Yes, you are clear.
Very good. So, can you tell me what is y hat I?
Is it b beta 0 hat minus beta 1 hat times
Plus.
by xi?
You mean plus, right?
Yeah, plus times by xi.
Very good. So that's all. Now, so what do you do? So this beta 0 hat and beta 1 hat are the estimators for beta 1, right? But then how do we get the numbers for those? So, okay, they are estimators, they are good estimators because, sorry, they are good estimators because they are unbiased, consistent, and efficient estimators for beta 0 and beta 1. And how do you obtain the estimates?
OLS.
Good. By OLS estimation method. Can you give me the? Can you tell me what is it that OLS does?
It minimizes the sum of squared residuals.
Which
With,
is
with I hat or disturbance hat squared.
not disturbance, not that's the
I mean,
residual.
sorry, residual. Yeah, residual hat squared.
And the sum is over all of our observations, right? In the sample. That's the sample size. And you are doing this with respect to this optimization, or in this case, minimization, with respect to beta hat 0 and beta hat 1. And you know that beta hats, both of them are in U hat, right? And then when you do this optimization, and I did not require from you guys to No, the derivation is easy, very, it's not difficult. It's in the class slides, but in the class slides, you take um, n equals 2, so that means you have only 2 observations in your sample, which is nonsense, but it still works for the illustrative purposes. But I mean, there's a better way to do this, and it is done using linear algebra, specifically matrices. Guys, again, am I clear?
Yes.
And then when you do this optimization, we obtain the estimates, right, of beta hat 0 and beta hat 1. Can you remind me those? That's covariance between y and x divided by variance of x. And once you have beta hat 1, then you can calculate beta hat 0, how? Y bar minus beta hat 1 times x bar. But then the thing is, okay, you have this, so what is your data? Can you tell me? Your data is what? Your data has this form. This is your observations. Here I have x, and then I have y. And then you have these observations, 1, 2, so on. Let's say you have 616 observations, let's say, and you have the numbers here, right? And because you have those numbers, you are able to calculate covariance between y and x because you have those numbers. And also you're able to calculate the variance of x, and you'll be able to calculate beta 1. This can be done in Excel, can be done in R, right? And then once you have, okay, you can also calculate y bar x bar when you have these x and y values. And then you can calculate beta 0 hat, right? Okay, then you have this beta 0 hat, and then you have this beta 1 hat, right? But then you are interested about testing the hypothesis about then once we have the estimates of beta 0 and beta 1, we are interested thereafter testing the hypothesis this is in plural because we are interested in testing different kinds of hypotheses about what?
The sample one?
About beta 0 and beta 1. Okay, so you have those, right? But the thing is, you don't know the true ones. You still want to know, what is it? Whether whatever you have are close to the truths, to the true ones. We never test hypotheses about the sample statistics. Instead, and please remember, we use the sample stats. To test the hypothesis about the true parameters. Population parameters. Let's do it. So let me remind you guys our model, which is this one. If beta 1 is 0, then we say xi it's not that we say, but that means beta 1 is 0, then x is irrelevant. So meaning that x does not affect that x means xi does not affect yi. So what does it mean? Not what does it mean, but when does this happen?
When both variables are independent.
Maybe this is not a good way to ask this question, but it still, I think, is an okay question. It happens when you find that beta 1 is insignificant. Sorry, to be more precise, that happens when not beta 1, but when beta hat 1 is not significantly different from 0, is not in statistical sense. Do you guys see what I mean? So, and this is this is the right time to introduce hypothesis test about beta 1. So we can hypothesize. What do I mean in statistical sense? Can you tell me? In standard deviations. We can hypothesize that beta 1 equals 0, right? And then we can test the hypothesis about this. Sorry. So how will I specify the hypothesis? It will be like this. H now, beta 1 is 0. What is 0? That's the hypothesized value. And the alternative can be that beta 1 is not 0, or it can be that beta 1 is, okay, that maybe it is like beta 1 is greater, 0, greater than 0, or less than 0, whatever. So in this case, this will be right-sided test, this will be left-sided test, but usually we do this. Okay, and what is the next step, guys? So the logic is the same as before. So the next step will be what?
Project.
The next step, how can you do it if you do not have an appropriate test statistic?
Do you have to find the t statistic or the
It's true.
t-stat?
Yeah, t-stat. So the next step is to calculate test statistic, which will be what?
Is it y bar minus? Oh,
Beta 1, you are not, so see, it's not, you are not testing hypothesis about y. Sorry, about mu of y. To test the hypothesis about mu of y, you were using y bar. Do you remember? And you were constructing the test statistic for the hypothesis about mu of y using y bar. Am I guys clear? But now we are testing the hypothesis about beta 1. It's not about mu of y. We are testing the hypothesis about beta 1. So you will be using an appropriate or a corresponding test, corresponding statistic in your sample, from your sample. The corresponding statistic from our sample corresponding to beta 1 would be what? Beta 1 hat that we already calculated above. And you subtract from beta 1 hat the hypothesized value, which is 0, because we hypothesized that the true beta 1 is 0, and then you divide it by what? Sigma of beta 1 hat. That will be our test statistic. The question is, do we know the answer is no. So then what do we do?
do we use the sample standard deviation?
Absolutely right. So we will use sigma hat of beta hat 1 instead of sigma of beta hat 1. So then the test statistic becomes beta hat 1 minus 0 divided by sigma hat of beta hat 1.
Can you move up a little? I just want to double check something.
Can
What is
you-
the statistics here? Shouldn't we get rid of the beta hat and put just beta 1? And same with the sigma beta 1, because we have the hat on the second one.
So whoever you are, this is like a really good question. Any question is good. but this is a good question, I would say. So the thing is, both heads are required, and I'll try to explain why. So when you are constructing a test statistic, what do? You take the sample stat, which is in this case, and you have to take an appropriate sample statistic, right? In this case, it's beta hat 1, and do you understand this? Because you are testing the hypothesis about beta 1, so you have to take an appropriate test statistic for that, and the appropriate test statistic for beta 1 is beta hat 1 that you estimated from the sample by OLS. Am I guys clear? And how do you calculate the statistic? You subtract the hypothesized value, which in this case we assume is 0, from the test statistic, and then divide it by the standard deviation, the true standard deviation of the beta hat of the sample statistic that we have. So the sample statistic that we have is beta hat 1. And you want to know what's the true standard deviation of beta hat 1. But the thing is, we don't know this. What do you do then? You use the sample standard deviation of the estimated beta 1. So this is estimated standard deviation of the estimated beta 1. By estimated beta 1, I mean clearly beta hat 1. And this is what we are using. And this is the true standard deviation of the estimated, So we are using this, right? So you see estimated, the word estimated twice. That's why you have double heads there. Here you see the word estimated only once. That's why you have this just one head here. But we don't know this because you don't have the data to calculate as a true standard deviation of beta hat 1. So I think I gave you an interesting note. Your task is to think about it.
Professor,
Yes.
since we're using the sample standard deviation, can we also denote the sample standard deviation as S?
Also, yes, that's absolutely true. So another,
Okay.
let me, then those are the notations, right? Which like the bad thing of having multiple notations for the same thing is that it sometimes causes confusion. So I don't really understand why there are those multiple notations for the same thing. I don't know. I cannot tell you. But both of those kind of notations are widely accepted. Okay. Another notation for this is what? S of beta hat 1, or yet another notation is S of B1. It's about knowing the ideas, and it's about knowing the intuition of what they really are instead. But it should also be consistent. If you are using that notation, use it everywhere. If you are using this notation, use it everywhere. Sometimes even I mix them, but I hope you guys understand. When I mix them, just let me know that, why are you mixing them, and I will not mix them.
Professor, what did you say here? Could you please?
What?
Yeah, I didn't understand. Like, could you please spell a little off? Yeah, so here, you said yet another notation is S101, or it's B.
S of B1 is yet another notation for the same thing. That and that, all of them are the notations for the estimated standard deviation of the estimate beta 1.
Okay, thank you.
Mm-hmm. Okay, so then let me do it in a different color. Let's try this. I've never used it before. So test statistic is what? Not for beta 1, it will be beta hat 1 divided by sigma hat of beta hat 1. This test statistic is for which hypothesis? Can you remind me?
Beta 1.
H0, where beta 1 is 0.
Very good, guys. I'm glad you understand.
Professor, how come you don't subtract by 0 in this one?
We do, but when you subtract, it doesn't change anything.
Oh, right, yeah. All right.
Yes, but it's a good note though, because we could also test the hypothesis about H null beta 1 is equal to 5. Then you have to subtract 5 from beta hat 1. But that's not what we are discussing right now. Okay, guys, how are we doing? Are we doing okay? Should I go back to explain stuff? It's okay if I have to, but if not, then I'll just go on.
I think we're okay.
Now, okay, so then the thing is, this one, first of all, you need two things to know. First, this test statistic is shown has student t distribution. Sorry, student t distribution. What does it tell you guys? So why do we care about that? Because, why do we care about this? Because we compare, because we take the critical values from the student t distribution. And what happens next? You just compare your test statistic to the student t distribution, and then you draw your conclusion. But one thing that you, and another thing that you need to know is the following. This test statistic, guys, do you see that I circled sigma hat of beta hat 1, right? I did circle that for a reason. The value of sigma hat of beta hat 1 depends on the assumption about the disturbance term. Let me write it here. The value of sigma hat of beta hat 1 depends on the assumption about the disturbance term. Specifically, whether the disturbance term is homoscedastic or heteroscedastic. Versus let me define this for you guys. Homoscedasticity means that the disturbance term, which is what? UI, right? Has a constant variance. And heteroscedasticity means that the disturbance term okay, y doesn't have a constant variance. The variance of UI depends on x, your independent variable. These are assumptions. Those are assumptions. Why are those assumptions? Can you tell me? Let me ask you, do we ever know, or will we be able to ever know whether the disturbance term has a constant variance or a variance, the variance is not constant?
No.
No, why? Because we don't know the values of EY, right? EY is a population term. It's a disturbance. We do not observe EY. Therefore, we never know whether the variance of EY is constant or not. Am I guys clear?
Professor, what do you mean by observe UI?
Let me explain. So do you remember this?
Yes.
Then, okay, then it means that if n is, let's say, 100 and whatever, 1010, right? Then how many values of UI are there?
Is it 100? 1010.
If you knew these values, would you be able to calculate the variance of UI? Variance of U?
Yes.
But do you know UI? So these values?
No.
Are you then able to calculate variance of U?
No.
Okay. But if you had these values, then you would be able to calculate it, right?
So shouldn't that be a capital N equals 1010, representing the population size?
I mean, you caught my mistake, but that makes me happy. It should be capital N. I will just I will do this. So see, that's a very good note. But that's the only mistake. That's a huge mistake. But you understand, right?
Yeah. Can I get your credit?
No. I mean, I'm sure you'll do well in the exam. If you notice this, then you'll be able to do stuff well. So you will not need it. But do you guys understand everything I said?
Professor, can you I was confused as to how the variance of UI can be variable. Like it can't be constant. Because
Very good, very good question. That's an amazing question. So, we first of all, okay, so how to explain this? So what is your x? X is our independent variable. So you ask the question, how can it be, how is it possible to how is it possible that UI doesn't have a constant variance? Okay, this is a deep question. I'm not sure if I'll be able to explain, but I'll try. So, let's see how to, give me guys 2 minutes because I'm thinking how to put everything together. Okay, let me postpone this question, or maybe even I can show you a figure where we have the figure where we have this the variances. So now let me share you a screen, another screen. This is, guys, from the class slides. Do you see the screen?
Yes.
Yes.
So this is like the end of like chapter 6, and chapter 5. So I'll contribute some time to understanding this heteroscedastic, the homoscedastic, and then next week we will have we have Monday, Wednesday, where I'll do exercises from these chapters 4 and 5 that will help us understand everything better. But for now, let's first of all, guys, I already said, and please remember that depending whether the disturbance term is homoscedastic or heteroscedastic, the value of the estimated standard deviation of the estimated beta changes. So that changes the test statistic too, because the estimated standard deviation of estimated beta 1, for example, is in the denominator. Am I, guys, clear? So you want to be sure whether you want to have an idea about whether the variance of the disturbance term is constant or not. You will never know that, but you want to have some idea about it. So there's a test about whether the variance of the disturbance term is constant or not. That is clearly based on a sample statistic. What is the sample statistic that corresponds to the disturbance term? Question.
UI?
U-hat, right? So U-hat is used to test the hypothesis about U, and then if you conclude that the disturbance term is homoscedastic, you will use one expression for calculating the variance of the estimated standard deviation of estimated beta, and if not, then you'll use a different formula. So those are the formulas. So I will go back to this figure. Simply, I want to just summarize what I'm saying. So guys, do you see this double heads?
Yep.
One is so if you take square root of those, you will get what? The estimated standard deviation, because this is the variance, right? So take a square root of it and they will get the estimated standard deviation of estimated beta 1. Similarly here for beta hat 0. Sorry, for beta hat 0 is this. So these are the expressions of how you calculate this sigma hat squared of beta hat 1 and sigma hat squared of beta hat 0, under the assumption that U is homoscedastic, that the variance of U is constant. So I give my students assignments that involve these expressions, and they have to calculate them in Excel. First, I don't tell them how to do this in R, because in R you can do this in a few clicks and that's it. But in Excel, you have to calculate every single term of this expression like this, that difference, and then square it, and then sum it up for overall I. So you have to understand this expression very well to be able to calculate these estimated variances and then estimated standard deviations. But the formula gets much more complicated if the variance of the disturbance term is heteroscedastic, and that's the expression. You have H hat is defined like this. So the thing is, I am also giving students assignments where they have to calculate every single term here to obtain this estimated variance of estimated beta 1. And most of the cases, guys, the disturbance is heteroscedastic. So almost always, I would say like almost always, you have to use these expressions. Do you really use them? No, because you do it in R. In R, this is just one click. But if you want to know what's going on behind that one click, you have to do this manually first, maybe once or twice, and then you will be using R. I will show both ways in the next week.
Is this something we could expect on the homework?
This is part of the homework, will be part of the homework. But as I said, I will do exercises next week that will help you guys in your homeworks. So what are these called? You see them, right? Those variances that are calculated by these expressions are called heteroskedasticity robust standard errors, because you are not calculating them this way, because then you would make a mistake. You are instead calculating them this way, and by calculating this way, you are correcting for the mistakes that you would make if you calculated the variances using this expression. So that's why in that sense, these variances of beta hat 1 and beta hat 0 are heteroskedasticity robust. Okay, they are robust. Heteroskedasticity robust. Robust means corrected for the heteroskedasticity in the disturbance term. Now let's go back to this figure. This is X, guys, right? Okay, do you now see the figure where I have figure 5.2? Do you see it?
Yep.
Okay, very good. Now, what do we have on this figure? And this is the answer to the question, to this question, guys, because it's an important question, as I said before. So the question that you guys asked me is, how is it possible that the disturbance term does not have a constant variance? I mean, I already answered this question here when I said doesn't have a constant variance means that the variance of the disturbance term depends on your X. Maybe on anything, maybe on something else too, but one of the examples could be that it depends on your X. What is the X? X is our independent variable.
Professor, are you using a different tab right now? Because we're still on the PDF.
Yes, I am, but I will show you guys. Then I will also share the different screen. So what I said is this. That I already said. So you asked how is it possible that the disturbance term U does not have a constant variance, and even before I said the heteroskedasticity, which means that the disturbance term does not have a constant variance. It can be because the variance of U can depend on your X. X is our independent variable. Now let me share the screen again where we have the figure. Right. And what you see in this figure is that the figure where we have our independent variable and our dependent variable. We also have the fitted line. It's not actually a fitted line, that's a big mistake. It's not a fitted line, it's a true line. Why is it a true line? Can you tell me? How do I know that it's a true line? Guys, I asked you a question. Please, if you can respond.
Oh, I assumed that because there was not, it was the equation it said was beta 0 plus beta 1 times X, and also going through multiple samples, I think.
No, but the second half is not correct. But the first one is absolutely right. And you see the functional form here, right? Because it says beta 0 plus beta 1x.
Yep.
Right? So you are right. That's why that's the population line. But do we only have this line, I mean, you don't have points here, but does it mean that the points are not there?
No.
No, clearly not, because the points are there. Simply for the illustrative purposes, they just omitted those. Okay. On the x-axis, we have measured our independent variable, which is in this case student-teacher ratio, and on the y-axis we have the test score, which is the dependent variable in this case. And it's really the problem is that I cannot write on the PDF, so I have to redraw this figure so that I am able to explain stuff. I know that there is a way to do it if I get access to some upgraded PDF, and I am willing to do it, but I cannot promise that I'll do it very soon, but I'll see. Okay, so this is our x, this is our y, and then we have points. Okay, guys.
Professor, I still see the PDF.
Now, I am just taking the values for a bunch of x. Bunch of x, I mean, let's say this is 10, let's say this is 20, let's say this is 28, let's say this is 45, whatever. Different values of x, okay? If I have like, if I write here, doesn't mean that points are not in between those values. Let's say here I have 15, and then I will clearly have something here too. Do you guys see how I construct this figure?
Yep.
And let's say these points, these white points, are the points from my population of size n. So then that means there is a line, which is the population line, right?
Professor, did you just like make random points?
Yeah, that's just for the illustrative purposes. And now, we have a lot of use, right, for the different values of x. So, for example, okay, let me use a different color. Which one? Let me use this color. So this point here is a point which is defined by expectation of y when x equals to 10. Do you guys agree with me?
Yep.
Okay. So let's say if this is my first point, so then this will be, if this is like observation 1, sorry. So then this will be what? That will be U1, right? So here would be Y1, right? and that will be y1 minus expectation of y1 capital not slash but the line conditional the x equals 10.
What area is UI measuring?
What?
What area is UI measuring? When you do that?
It's not a measure, it's a difference between actual y and this fitted, not fitted, but the expected y. Do you see? So let's say, look at this point. Let's say this is observation, whatever, let's say observation 8. So then this point will correspond to what? Expectation of y8 conditional that x equals 45. But this point will correspond to what? y8, right? And then the difference between these 2 points will be what? u8, which is y8 minus expectation of y8 conditional that x equals 45, and that's what I did here, but for observation 1. Am I clear? But you have a lot of, so those are what? Disturbances, right?
Yep.
Can you calculate variance for that? Disturbances? Yes.
Yeah.
And it will be a number, right?
Mm-hmm.
But that will be for x equals 10, right? Can you do the same thing for x equals 15, 20, 28, 45?
Yes.
You will have to just calculate this, right? The variances of the disturbances. Same thing here.
So that's how you get variable or not constant variances for you.
I think now you answered your question, but the thing is, would you expect that the variance that you would get for x equals 10? So would you expect that the variance of u conditional that x equals 10 is the same as the variance of u conditional that x equals 15 and so on?
No.
No, that is almost never true. And that's why we almost always have heteroscedastic U. And that's why you will always be using, now let me change the screen. We'll always be using this expression, not this one, but that expressions for calculating the estimated standard deviations of estimated betas. Am I clear, guys?
Yep.
Very good. On this figure, you have not only the points, but also the distribution of the disturbances, right? If the distributions have the same shape, like exactly the same shape, then you have the same variances. But if the disturbances have different shapes, like see the disturbances, not disturbances, the distributions, the density functions get wider and wider, that becomes the variance. That means that the variance of the disturbance is not constant. I explained this in much more simpler words already without using these densities, right? But yes, and I hope you guys get the point, right? So today's class is over. So we explained, we finished, we covered chapter 5 I will assign homeworks about chapter 5 later today or tomorrow, next week, next Monday and Wednesday. We will solve exercises from chapter 4 and chapter 5. And that will help us understand everything in more depth. So let me save this. So before I guys let you go, do you have any questions?
No.
Very good, but you know that you can always reach out and let me know if you have any questions, concerns, and I will of course try to. I will definitely consider them. So guys, then I wish you a good weekend, and I will hopefully see you all next Monday. Have a nice day.
Have a nice day.
Professor.
Professor, I actually have a really quick question.
Sure.
So can you just scroll up to the chart or the graph you just made?
Yes. Here.
Yeah. So I just wanted to know. So the points above the line and below the line, are these the disturbances?
Yes. So those are like these white points are the points, actual points, right? So
Yeah.
let's say this is observation 7. Let's say this is observation 6, whatever. Let's say whatever, right? So can be 1, can be 2, whatever, right? So then this will be the disturbance that corresponds to this observation. That will be the disturbance that corresponds to the observation. That disturbance will be negative, that disturbance will be positive, right? Because
Okay. All right.
Professor, so will we try to solve problems using RStudio too?
we will definitely be using R as well, but I'm not sure if I'll start using R because I want you guys to do these problems yourselves, applying those formulas, and then I will tell you how to do those in R in a few clicks. But let's see, right? So try your best, and I will definitely, of course, teach you guys how to use R for these problems too.
And for the midterm number 2, so we do not need R for that, right?
No, but yes, but you may find it handy, but you definitely do not need it for that.
You think Excel is enough, right?
Excel is fine.
Okay.
Would using R like speed things up on the midterm? Like, would it be a better way?
It entirely depends on you guys.
Oh, okay.
So if you find it quicker, easier to do stuff in R, if you have experience in working in R, then it will probably be faster, better, but both work well.
Right. So, Professor, you also mentioned that we'll be using Excel to find like covariance and stuff.
I will show you guys how to do those in Excel too. I think I already solved a few problems that I have not solved with you, but I solved it in the previous courses.
Okay.
You get enough practice. Don't worry.
Right. So I wanted to know if there's like a specific function on Excel that.
No, that's right. There's no specific function in Excel that calculates. No specific function in Excel that calculates heteroscedasticity robust standard errors. Estimated robust standard errors.
All right, Professor, my last question. You kind of went over this in the beginning of class, but really, like, I don't see what's the difference between the disturbance and residual notation.
Head, UI head, and they are different.
Yeah, it's very subtle. I couldn't catch that.
Very subtle, but very important. They are like entirely different from each other, and they are defined like this. That's the disturbance, that's the residual, and everything. The details are here.
Okay, that makes so much sense. All right. Okay. Thank you.
No problem. So guys, if you don't have any more questions, I will let you go.
Professor, I have a question.
Yes, sure.
Is the test cumulative?
No.
Okay, and my second question is how many questions are on the test?
18.
18? Okay, thank you.
Thank you, Professor.
No problem, guys. Thank you very much. Okay, then I will also leave and see you on Monday. I think we have a regular class on Monday, so if there's anything, I will let you know. But hopefully, see you all next Monday. Have a nice day, guys.